So our first presentation is by Professor Vesna Terzić from California State University at Long Beach, from USA. And Vesna is connected with several universities, institutions that are the representatives are here. She's first of all a graduate of this University Faculty of Civil Engineering, University of Belgrade. Then she did her master's thesis. She worked on her master's degree from the EFEHR in Skopje, and finally she did PhD at University of California, Berkeley, with Professor Boža Sredinović. So she will be talking, as you can see, of a novel framework. And welcome, Vesna. We're very happy that you're here.
Good afternoon, everybody. It is my great pleasure to be here today. Being back at the university that I'm coming from, it's very special, and also seeing so many people that I worked with, collaborated with, or learned from is great. So today I'm going to talk about recovery, but from a different perspective. So here I'm going to show you the framework which I developed that evaluates recovery from an individual building level perspective. So we look at one building and we do like detailed analysis to evaluate its performance. The work that I'm going to present here, I did it together with my students, Penny, Daniel, and Doc. In addition to them, we had like a number of academic and industry advisors without whom this work wouldn't be possible. So we had on board general contractors, facility managers, building inspectors, structural engineers, all who had a great experience in a 1994 earthquake which happened in Northridge in California. So we were able to learn from their experience and integrate their knowledge into our model. So the motivation for this work started by looking at the current code, right? And the way we design buildings for seismic actions is more than 40 years old. And in our models, what we do, we think of materials as elastic, and then we apply some simplified load which should represent ground shaking. And then we apply a bunch of coefficients to make up for all these big assumptions that we have in our code. And when we design using the code standards, we design for our buildings to undergo damage, but the damage is controlled so the building would not collapse, right? So the intent of the code is to safeguard buildings from failures and from loss of life. But the code is not concerned with limiting the damage or with maintaining the building function after the earthquake, right? So as a result, what we see in earthquakes, we see that buildings will have significant damage, which takes a long time to repair. Recovery lasts for a long time, and all of this generates high financial losses. And here, when we're talking about losses, we're talking about direct losses from cost of reconstruction, and also the indirect losses from the lost businesses, right? So here we see a picture from 2014 Napa earthquake, which was magnitude 6 earthquake, not strong, but it generated over 6 billion in financial losses, where majority of these losses came from long time to recovery. Right? So those are indirect losses. Here's another picture. This is from Christchurch earthquake 2011. And we see a disturbing amount of non-structural damage. So although the building did not collapse, it was structurally stable, the amount of non-structural damage is very disturbing. So, and it also is threatening to the occupants. So now we see a dramatic impact of an earthquake on occupants, on building owners, and then on a community as a whole. So looking at the new construction, right, what we can say with high confidence is that new construction is probably structurally safe. However, when it comes to resilience or its ability to quickly recover after an earthquake, we know that they are not going to be resilient because we know that we are designing those buildings to undergo damage, so therefore there is no chance for them to be resilient. So, with a performance-based design and our ability to evaluate everything you see on the picture, right, now that we can map structural responses into damage and use the damage to evaluate recovery process and financial losses, we can change the way we design our buildings, right? So we can move towards resilient design, where by controlling the damage that the building will experience in an earthquake, we can assure quick recovery and then minimal losses. So that's the goal. And if you're wondering how we can do this, FEMA, which is Federal Emergency Management Agency in the United States, has invested like significant amount of resources and provided it to engineers to create the tools for the loss assessment analysis. And their greatest contribution lies in development of the fragility library, where they are, for all structural and non-structural components, they're mapping structural response into the damage, right, for each building component. So let's say for these walls, if an earthquake happens, they're going to tell you how much damage you'll have, and then they will tell you how much it costs to repair, as well as how long it takes to repair. So now when you have all this information, you can use it however you like it, right? So the easiest way would be to, if you know for each of the building component how much is damage and how much it costs to repair it, you sum up all the damage within the building and you get the total repair cost for the building, right? However, when it comes to repair time, it's much more complicated than that because there's so much involved in repair of the building, from inspectors coming on site, evaluating the damage, engineers, if needed, redesigning the building or providing retrofit solution, then going through the permitting process and so forth. Once the repair starts, you have like so many crews that you have to organize within the building, and it's complex, right? And that's something that my research group did. So our goal was to try to use the information that FEMA P58 provides, which is the damage assessment, and see how we can use that information to describe the recovery process of a building. So today, I'm gonna give you just a big picture presentation of the framework. We call it EFEHR. It stands for functional recovery, right? That's our goal, to evaluate functional recovery, time, and all that contributes to it. And then I'll provide an example of a tall building in Los Angeles to show you the type of information that this framework provides. And I'm gonna close it with ongoing and future work. The framework is fully probabilistic. It's a building level, meaning we do it for one building at a time. And what it does, it describes the recovery process, which is schematically shown here. So what it includes the lost function right after an earthquake because of the damage, right? You're gonna lose some of the functionality for your building, which we measure as the percentage of the lost area, or area that you cannot use within the building. And then we have the recovery path and the duration of the recovery. To evaluate that, we have developed three main methods which are integrated together. The first one is the one which we use to evaluate functionality of the building right after an earthquake, taking into account the damage that the building has experienced. And to define it probabilistically, we call it functionality limit state, right? That tells us how much function there is. And then we have a mobilization time model, which tells us how long it takes for a building to prepare for the actual repair. and then repair time model, which tells us how long it takes to repair the building. So with all this combined together, we can plot a picture like this, right? Which we call recovery curve. This framework is in line with performance-based earthquake methodology, where you start from the hazard analysis, use that information within your numerical model of the building, knowing the structural response of the building, then using FEMA P58 information, you do damage assessment of the building, and then you pass it into our framework to find how long it takes to recover. So the first method of this framework is one where we are evaluating level of post-earthquake functionality, like how much of functional area you have within a building. And to do that, we use whole tree analysis, where we, for a building, which is a complex system, we recognize all the subsystems which are necessary to function for the building to function as a whole, right? And here we are showing all the core building systems which are necessary for building functionality. For example, HVAC system, which provides ventilation, cooling, and heating, electrical power, so forth, all the way to the structural system itself. And then each of these subsystems of the building has its own fault tree, which then breaks it into its all individual components which are necessary to function for that system to function as a whole. And here I'm showing an example of the HVAC system, whose primary function is ventilation. Then secondary functions are heating and cooling. However, for any of these systems to function, we need power, right? So we need electrical system to work. And if any of them fails, we are calculating their impact on the functionality of the entire HVAC system. In the United States, heating and cooling really depend on the season of the year, of the function of the building, and they're not always necessary for the building functionality. So we're introducing those switches here, which we can use to turn them on and off from our analysis, depending whether we need them or not. So if ventilation is the only one important, we turn off cooling and heating from our analysis. And here is the result of that functionality analysis. Here on the left, we see this figure, which shows us functionality limit state. So for example, here, if you look at the median, we come to intensity level 1, shown here in blue. We come down and we read the loss of functionality for the building. In this particular example, it's 35%. So what this means, it means that there is 50% chance that this building will lose 35% of its function, right? And then another type of information that we can generate using these data is the next one on the right, which is probability of attaining a certain functional state. And here we have introduced 3 different states. One is no loss of function, meaning the building is fully functional, everything's fine. Then there is a partial loss of function, which can be any number between 0 and 100, right? So it can be 35% functional or 70% functional. And then full loss of function, meaning building has to be closed. It's not going to be able to provide any function to its occupants. And then if you look at this, for example, here at intensity level 3, whatever it is, it's like here representing a very strong earthquake. We can read the states in probabilistic way. So here, looking at the red line, which is full loss of function, we see it's almost 50% chance for this particular building to fully lose its function, and then another 50, around 50% goes to partial functionality. And this gives us an insight, like a big picture insight, like what state this building will be in after an earthquake. So now with the functionality analysis, we do evaluate that level of functional space in the building, but we also tag all building components which are damaged enough to affect functionality or to impair functionality, right? So now these components, which are damaged enough to affect functionality, go into our repair time model, where we evaluate how long does it take to repair those components, right? And repair time model has two methods. So one is repair scheduling, and the other one is resource scheduling here. Repair scheduling uses critical path method, which is widely used in construction industry. So we are adding repair system to that. And how does it work? It starts by defining the network logic of repair, where for each repair activity or each component that's being damaged within the building, we define its predecessors and successors, meaning what has to finish repairing before I can come in and start repairing this component, and which component comes after that one, right? So that's called network logic. And then with that, we look at the number of damaged components in the building for every component that can impair functionality, and then assign realistic workforce to that, right? If I have little repair to do on one component, my crew is going to be smaller. Then I have like lots of damage in the building at the same time, then I'll send larger workforce to repair it. And after we are done with scheduling repair, you have to make sure that there's not too many workers at the same time on the same floor, so that you do not run into labor congestion, right? So all crews, they need to have sufficient space around them to do the repairs, and we have developed here a resource scheduling method which optimizes the workforces within the building so that they have the minimal impact on duration of the project. So we're going to be either reducing the number of workers assigned to one activity, or we're going to be shifting them around, but making sure that the total duration is not changed a lot. So the final result of this is Gantt chart, which I'm showing here. And what that shows us from the start of the repair to the end of the repair how long it takes. This is the duration of the repair project. And then also it tells us what are the components that are governing this repair project. In this particular case, we see this dark or navy blue color here, which here are some slab column connections. So this gives us information on critical components within our building that we have to, take into account if we want to minimize the damage. This is where we should put our effort into protecting this type of components. So this repair scheduling model is very flexible. It can be applied to any region, any country, any market, because we can simply define the way how in a certain region the repair is going to be done, use it within the model and get the result. So here I'm showing just a simple example from the tall building that we did, where we repaired 4 floors simultaneously for all structural components. So you wouldn't do that one floor at a time, you would do several floors at a time. Non-structural components, we did 2 floors at a time, and equipment 1 floor at a time. And this is all based on the recommendation from the general contractors. We didn't come up with any of this number, or we didn't come up with a schedule. This is information we get from people who know how to do repair. Also, this information we also got from the contractor, which we use within our model, and this tells us, depending on how severe the damage is for each of the components, how many workers to send in the building, right? So depending on the amount and severity of damage, different crews will be sent to repair it. And last component of this model is mobilization time model. So this model calculates the time from the earthquake until you start repair. And this one includes all activities that need to happen for the repairs to start, right? And I have already mentioned some of them. I mentioned the inspection, engineering, permitting, but there's many more than them. But what's unique to this model is that here we are using 3 states that could possibly happen within the building that are going to define which activities will be triggered and how long will they last. And these 3 states are repairability limit states, which is the first one, where we ask, is this building repairable at all, or do we need to demolish, right? If we find that the building is not repairable, then recovery time is equal to the replacement time of the building, right? That's very simple, straightforward. And this information we acquire from FEMA P58. FEMA P58 tells us this. The next question we ask, okay, building is repairable, do we need detailed inspection or not? So, and if we see that the building is damaged to a level where it needs detailed inspection, then we are going to activate all of these blue blocks or activities to get ready for the repair. If the detailed inspection is not needed, it becomes a little bit simpler. We ask, is functionality compromised? Because if functionality is not compromised, recovery time is 0, that's the end of the story, we are good, right? But if you do not need detailed inspection, but still functionality is compromised because maybe some ceiling tiles fell off somewhere and that space cannot be used, or something similar, we still need to get contractors on board, we need to clear up the space and so forth, so we need to take into account all those activities that need to take place before we can start fixing ceiling, for example. So I already told you how we calculate functionality. So now I'm just going to show you how we do decide whether we need detailed inspection or not. Again, we use fault tree analysis, where here we are defining all things that could trigger detailed inspection. So first and foremost is the state of the building, right? So if the building has unsaved placard, which is a red tag, or if it has severe damage, we're going to close the building and inspect it before we let anybody use it, right? Or if there is a severe non-structural damage that can hint off to the presence of structural damage, again, the facility managers of buildings will close the building and say nobody can use it until we inspect and make sure that the building is stable, right? And for example, what could be the trigger for that? So for example, if you have cracking and separation of exterior walls, they might be wondering, okay, this is so much damage, what's happening to the structure, right? Which is hidden underneath it. Or if you have huge crackings of partition walls, again, what's happening to the structural components in that case? Okay, so with this, we have the framework in place. We know how to map all the damage within the building to evaluate all these different components necessary for the recovery evaluation. So I now want to show you on a quick example of a tall building how this data look like. So we used an existing design of a building, which is a 42-story located in Los Angeles. It has also 4 underground levels. For this building, they selected the ground motions for 3 different intensity levels. They are called service level earthquake, design basis earthquake, and maximum considered earthquake. Each one had 15 ground motions that represented that level of hazard. And then we built in OpenSeas, which is an open source software for numerical analysis, we built a nonlinear model of the building. It was a very fine model that can, as realistically as possible, predict structural response for all these earthquakes. So we did run all these earthquakes through the building, and here I'm just showing some responses which are important for damage analysis, right? So those are story drifts, residual drifts, floor accelerations, coupling beam rotations, and pier rotations. So we use this information to map this into building damage, to do damage assessment. So after doing damage assessment and plug the damage data into our framework, we are going to get some results. So here I'm showing you the first set of results that we find very important. It provides us insight on the functionality of the building right after an earthquake, and it also tells us what is it that's problematic in the building that we are analyzing. So here what we're looking at the probability of attaining different functionality state in a building, where green is no loss of functionality, orange is partial loss of functionality, and red is full loss of functionality. So here at the bottom, I'm showing the results for the building system, and you see this particular building doesn't do very well, either in design basis earthquake or maximum considered earthquake. It will lose its functionality fully right after the earthquake. It's designed to code, but will it be functional? No, it won't, right? And then not only that, but we can see what is it that drives the loss of functionality. And then here I'm showing in these other blocks, I'm showing the data from different systems within the building. And if you compare the results for the building system to the subsystems, we see that it looks the most like this one here, right? Which is the structural subsystem. So you see that in this particular case, it's structural damage that's governing the loss of function. All the other systems are non-structural systems, and they're doing much better than the structural. So if we are to improve resilience of this building, where we have to invest, we have to invest in the structural system to make it more resilient. The next set of data that we develop are functional recovery fragilities. So here on the left, we see them for 3 levels of seismicity that we considered. And why is this important? Because then using these fragility curves, we can pick out any outcome of interest and find what's happening to the building for that outcome. Typically, we use median and 90th percentile outcomes to find the range of behavior of the building, right? And here on the right, I'm showing, for example, total recovery time for median and then 90th percentile for these 3 different hazard levels, right? So now, I'm going to go a little bit deeper. I'm going to zoom in and provide some more detailed information to see why is this happening. And first, important information can be received from this recovery curve chart. So this one has lots of information. So first of all, it tells you for selected realizations, again, median and 90th percentile is what you're looking at. It's going to tell you how much of functionality is there in the building right after an earthquake, and we see that right after an earthquake, this drops down to 0, meaning functionality has been lost, right? And then the rest of the curve shows you how the building recovers over time, and it tells you how much time it takes to fully recover, right? So for this particular building, for the design basis earthquake, we are predicting that it's going to take 8 to 13 months to fully recover this building, right? To get it to be working again. However, you see that the bottom floors are functional after 120 days. So if somebody wants to use the bottom floors of the building, yeah, they can go ahead and use them and wait for the rest of the building to become functional. Then the second chart here shows us, for the median realization, it shows us the mobilization time activities that are going on. And from this, you can see what is it that's governing that mobilization time or the preparation for the repairs. And if you see what is the largest, which bar is the largest, it's going to be this one. So that's the one where you have to do the detailed inspection of the building, prepare engineering and architectural drawings, and then do the permit of the building, right? So that takes a long time. And then once we are ready to start repair, this last chart shows you the repair schedule, which shows the total duration of the repair, but also what all has to be repaired to bring the building back to its function. And again, here you see these slab column connections being problematic and governing the recovery process. So now, this information that I presented can be used in so many different ways. It can be used to switch design from how we do it now towards something more resilient. And you can decide the level of resilience that you want for your building. And again, this is targeted towards individual owners or developers or investors who can set up their goals, and engineers can use the framework to meet those goals. How I envision that, you might start from your basic code design. Now you have for this type of analysis, you need to have a sophisticated model. It has to be nonlinear model. It cannot be elastic. So you model your building nicely. You select ground motions for it. You run through the building, find the response, evaluate damage, see how much repair is going to be needed, and that's going to relate to recovery time, financial losses, and if what the stakeholder sees is not a nice looking picture to them, what we can do, we can iterate, right? We can iterate design until we get to meet their performance objectives. And this iteration can be done in many different ways. My group is working on developing an algorithm, optimization algorithm that we wrap up around this and that does find the solution, optimal solution itself. That's one way. Sometimes engineers might have, so much more experience and better awareness and quick hints as to, oh, I see what's the problem. If I make this change to my design, I can very quickly find a better solution. That's another way. So we can show them the pictures of the damage of the components that are critical, and then they can suggest ways to improve it very quickly. Another way this can be used is by integrating this with frameworks for quantifying resilience at the community level. And here is an example of EFEHR, and Nicola will be talking about this very soon. So what we are currently doing with Nicola and Boja, we are building an interface between EFEHR, which does community evaluation of the resilience, with EFEHR, which does it for individual buildings. So we are interfacing the two, having them talk to each other. They collect important information from our model and use it to evaluate resilience at the community level. In closing, I want to say that this framework provides opportunities for many other research topics. So, for example, United States health monitoring is a big topic. We are instrumenting lots of buildings from the get-go, new buildings which are newly constructed. And if we have that information after an earthquake, there are ways to map them into damage, which then can go into our model and quickly evaluate functionality. And that information can be used to prioritize the management of the disaster. Also, all we need here is the damage, right? To evaluate how long it takes to recover. So if you have any other disaster other than earthquake, if you have a flood, if you have fire, you can use that information of the damage, plug it in our model, and evaluate recovery, right? This doesn't change. Our part doesn't change. It's just the input that we are that's being fed into our model that is changing. And with all of this, what I see to be happening in the future, that something like this could be used not to look at individual buildings per se, and then let individual stakeholders or investors make better building, for the community to contribute or to benefit from this. The way to move forward would be to use something like this to come up with design requirements that engineers can easily use in their offices to design more resilient buildings. So this framework can be used on the back end to develop some curves that engineers can just read off the important values from to say, if I want my building to be resilient, I should restrict drifts to 1%, right? So they don't need to know anything that's been going on here, just some structural responses that they need to use to make more resilient buildings. And this would be all from me. So if there are any questions, I would be happy to answer.
Thank you very much, Vesna. Any questions, please? Go ahead.
Thank you for your presentation. I want to ask you about, because in the beginning you said that all the information regarding scheduling of repairs and recovery, etc., was based on interaction with basically with contractors. Do you were you able to get reliable data regarding demand surge and its effect on after disaster? Because it won't affect one building, it will affect a lot of buildings, especially in urban areas like, for example, downtown LA. And the effects of demand surge on both on schedule and increase of the price of the repair. Because in my experience with interacting with clients, that they own buildings then, and they want to know how this is going to happen after the recovery, basically. Very often they're quite optimistic that the earthquake happens, and on the other day they can start the process and this is never the case, of course.
Thank you so much. This is a great question. Yeah. So these are all important points, and there is a way to evaluate depending on the size of the disaster to multiply whatever losses we are calculating, and these are built into FEMA, which tell you depending on the size of the seismic activity, what multiplier factor you should. It's simple for now. It could be more sophisticated, but there is a way to adjust for the price change right after a disaster, right? And that's going to depend on how big or how affected the community is. The second part of the question about surge demand, this is a great question. This is something I'm now working with Nicola, so that the idea of using his community resilience framework, where he looks at the supply and demand and consumption, and to schedule resources knowing what is the surge in demand. So this is an ongoing work, and after you hear Nicola's presentation, it might be kind of clear how we are going to combine the two to produce some better information.
Thank you. Perhaps in the interest of that, please go ahead. One question.
Very clear, interesting presentation. I just had a question about the external systems in place in the building and in fault analysis, for example, power supply, and that in itself is a complex network. If there are simple methods to account for the failure of that building, how important is that?
Thank you very much for another great question. This was about externalities that affect the functionality of the building, electrical power system, which are outside. If they fail, how is that going to affect the building? And again, thanks to Nicola, we are going to, his model captures everything that's happening at the community level, and that information is exchanged from his framework into my framework. So through communication, we can capture effects of externalities, including water supplies, power supplies, and so forth.
Thank you very much.